Welcome back, Math 1910, Calc 1. We are in Chapter 3, Section 8. Going to go through Newton's method, alright? So Newton's method is really just a way that we approximate finding a zero, alright? So it's just a technique that we're going to use, and we're going to use tangent lines to approximate the graph of the function near its intercepts, okay? So, remember for what we're looking for is, a sign change from f of a to f of b. All right, that was the intermediate value theorem, so that we could conclude there was at least 1 0 when we went through the function. So if f of a was negative, f of b was positive, we knew that somewhere between a and b that there was a 0, right? It crosses the x-axis. Or if f of a was positive, f of b was negative, we still know that it went through across the x-axis right there, so that we had a 0 that we came through. So, using Newton's method, okay, we're going to use that to kind of estimate a 0. So we're going to take some estimates. We're going to get close to the 0, just by our guess, but we're not necessarily going to pick the 0 because it might lie between like two whole numbers or things like that. So what we're going to do is when we use Newton's method, okay, we're going to base it on the assumption that the graph of f and the tangent line at x of x1, f of x1, both cross the x-axis, okay, at the same point. Okay, so that's what we're going to base our approximation on. So we are going to estimate, or select, arbitrarily pick a x value that's close to where we think that it crosses the x-axis, and then we're going to do what we call iterations as we go through there. So we're going to do a couple different trials as we go through this. So remember, to find the tangent line, we use point slope. Okay, remember that's y minus y1 equals m times x minus x1. Well, in our case, we're writing it in function notation, so it's going to be y minus f of x1, which is just y minus our y1. Okay, f prime of x1, that's our slope, right? That's the m, and then times x minus x1. So in order to use this, it's really essentially Newton's method. We are just calculating kind of slopes over and over and over as we are choosing, closer and closer to where we think that it crosses the x-axis. So if we look at it, all right, and we solve this equation for y, we end up with y equals f prime of x1 times the quantity of x minus x1 plus f of x1. It's really just, essentially point slope. So let's, take a look at it. If we're going to let y equals 0 here, and we're going to pick an x1 that's, close to where we're crossing the 0. Remember, y equals 0 is where we're crossing the x-axis. Okay, so that's why we have to make sure that we let y equal 0. So a lot of, just basic algebra skills as we go through with this. Okay, but, say we want to make more than one x estimate. All right, so if we say our first one that we want to find is x, we can use x1 minus f of x1 over f prime of x1. And then we want to get closer. We want to get a more accurate value. We would make a new value, x2, based on our approximation that we calculated from x1. Okay, so we'll create that new value as we go through and do multiple iterations of what's going on. So, we can find x2, x3. So as we substitute in our first, use our prior estimate to get closer and closer to our newer estimate. Alright, so we can use the previous values. So like x2 involves x1 minus f of x1 over f prime of x1, right? That creates our x2. x3, I'm going to step forward back to the slide here. x3 is x2 minus f of x2 divided by f prime of x2. We are using the x2 that we calculated here in this estimate, in our second estimate, okay? So as we get closer and closer, we do more iterations. We repeat the process to get closer and closer. Okay, so here's our definition for everything. So if we use Newton's method for approximating zeros of a function, okay, we have to let f of c equals 0, right? Where f is differentiable on an open interval containing c. Then to approximate what that c value is, right? F of c equals 0, that's us finding the 0, where it's crossing the x-axis, okay? Step 1, we make an estimate that's close as we can get to c. Okay, and it helps if we're looking at our graph on our calculator. So you might want to substitute the function into your calculator and take a look at the graph and see, what's close. Because, we're using approximating zeros, for values that are between whole numbers or things like that. So we want to determine what a new approximation is. So we're going to use Newton's method here, right? X to the n, or x subscript, right? N plus 1. So that's our iteration, equals xn minus f of xn divided by f prime of xn. Remember, n is going to be our iteration, our 1, our 2, our 3, our 4, however many times that we're going through this, all right? Because this is successively applying this approximation method. That's why it's called an iteration. We're doing it over and over and over. Okay, so we're going to, have our absolute kind of final approximation, based on how many approximations we get, how close we're getting to the true zero of the function, based on the number of digits that we have remaining. So let's just take a look at an example here. Okay, we want to calculate 3 iterations of Newton's method to approximate the zero of f of x equals x squared minus 2. Alright, so we have a parabola that's going down, or it's shifted down 2 units and it's still convex or concave up. So we want to start approximating using x1 equal to 1. Okay, so we have our function. We have to take the derivative of our function. So we have to find f prime of x, which is 2x here. And then we have our x1 value, and then we have to evaluate 1 into the original function and into the derivative. So if we substitute 1 in for x here, we get 1 squared minus 2, we get negative 1. Okay, and then if we substitute 1 into the derivative, we get 2 times 1, which is 2. Okay, so that would be our first iteration as we go through here. Okay, and we're just substituting into this piece. So we found, or we're given the original function, we found the derivative, okay, and then we're going to use x1, we're going to substitute in our 1 there. So literally we're just plugging in these values. So I'm going to step forward. So if we do that, right, when n equals 1, our first iteration is we plugged in x equals 1, right? And we got 1.5. That's the column all the way to the end. So when we evaluated f of 1, f prime of 1, and we used the value of 1 minus that, we ended up with 1.5. That now becomes our new xn for our second iteration. So now we're going to find f of 1.5, f prime of 1.5, and substitute it back into here into the iteration formula. Very, very simple, guys, when we do this. It's literally whatever we get out. So the next time when we do our second iteration, we get 1.41. So now we're going to use 1.41 to do the next iteration. So we got to find f of 1.41, f prime of 1.41, and then do 1.41 minus the ratio of f of 1.41 divided by f prime of 1.41. So you can see it's all made in the table here, and you can see as we keep doing more iterations, we get more exact. But look, our first iteration, right, we chose 1. We thought 1 might have been close, okay? And then we get closer to 1.5, and then we start really focusing in. It ends up being 1.41, which we know 1.41 is the square root of 2. Okay, so we know the zeros of this function are plus or minus square root of 2 anyways, right? Because if we step back and look at the original function, x squared minus 2, if we set that equal to 0 and solve for x, this is kind of the same thing, right? We add 2 to both sides, and then we square root both sides. We know that the answer is plus or minus the square root of 2. But we can use Newton's approximation, all right, to calculate that it is 1.41 and to verify it. It takes us 3 iterations to start getting there, but we know that the square root of 2 is 1.41. So just a different way of actually calculating the zeros using calculus. So remember before, it's kind of dummied down algebra before when you're doing it. You're really kind of applying the rules of calculus when you've done it in algebra. But if we take a look, right, if we take the square root of 2 and put it in our calculator, out to 6 decimal places, you're going to get 1.41, all right, 4214. All right, so after 3 iterations of Newton's method, we're approximately within 0.000002 of the actual root, if we look back at the table here. Okay, because it's 1.414216, all right, and the actual root right there is 1.414214. So the real root's 14, all right, we calculated 16 within 3 iterations. Okay, so that's really kind of the difference. So you can see, if we take a look at the iteration process here, x1, we chose 1, all right, we were off a little bit, and then we saw that x2 was 1.5, and then our next iteration got us to 1.41. So we can see closer and closer, the more iterations we do, the more exact value we get. Okay, so what we're really doing and thinking about here is, as we are approaching a limit, it's really what we're doing. We're saying that it's converging. Now, Newton's method doesn't always make a nice convergence sequence, okay? It can fail a couple times. So right here is an example of where Newton's method fails to converge, all right? Because f prime of xn ended up being 0, okay? So we got it kind of depends, okay? And we have to, when we have an issue like this where f prime is 0, we have to make sure that we maybe choose a different value to start with. Choose a different approximation to kind of overcome this. Okay, so Newton's method will fail to cover if the derivative is 0 in that sequence. So if that works out and comes out that way, you have to choose a different x1 value that you start out with. All right, so that's a way to get through when that happens. Okay, let's do another example where Newton's method doesn't work. Okay. We have the function, okay, f of x equals the cubed root of x, right? We rewrite that as x to the 1/3. And we know that it's not differentiable at 0, okay? So we want to show that it fails to converge at 0.1. So we have to take the derivative, okay, chain rule, power rule, derivative here, right? It's not really chain rule necessarily, but just using the power rule, right? So we get 1/3 x to the minus 2/3. All right, when we start evaluating those things in, okay, we're going to substitute x of n is 0.1. So we have to find f of 0.1, f prime of 0.1, all right, and then subtract that ratio from 0.1, okay? So we can see as that happens, we're going to get xn minus 3xn, okay, and get negative 2 times xn, if we just kind of work through that. So we can see here, all right, where it's not going to converge, okay, at 0.01. So we can look at your first estimate, and then look at your last estimate, as we go through the table here. We're going, negative 0.2, negative or positive 0.4, negative 0.8, 1.6. And it makes more sense, if we take a look at this graphically, it's not really converging here. Why? Because the limit, as we take a look at this, we're going to get a vertical tangent line there. So there's where we're going to have some issues, okay? If it's not going to work out for us, right? Because it's only going to converge for every x value other than the actual 0 of f. All right, so this is just another, a reason where Newton's method doesn't quite work out, okay? So if we want to produce the convergent and overcome that, okay, we're going to use this, right? So we have f of x times f double prime of x divided by f prime of x squared, okay? That's our condition. It has to be less than 1 for conditions of convergence if we're on an open interval containing 0. So this one's going to get on, more advanced algebra for us to do this, okay? So over the years, you've learned different ways for finding zeros, okay? So sometimes we factor, sometimes, we are easily just set it up, find the zeros, set it equals 0. Other times you've used the quadratic formula, all right, where you've used the leading coefficients of the polynomials to find the zeros and such as well, all right? And we can't use, elementary algebra to solve everything. Sometimes we have to use Newton's iterations and things like that. So if you have a function, all right, that requires more algebraic techniques, we can use Newton's methods and things like that. If we have an exact solution that's written in terms of square roots or cube roots or fourth roots or things like that, we make sure that we call it a solution by radicals. Okay? Don't get too lost in this section. It's really just being able to kind of understand Newton's method, do a few iterations with it to see if you get close to what the real zero is. Alright, I'll go through some more examples in class, guys, if you watch the live stream or if you're in person or whatnot. But like I said, email me if you have any questions. Let me know if we need to Zoom meet, team meet, or anything like that. Else, guys, have a great day, and I will see you in class.